Okay. Well, I guess we might as well get started. In this discussion, just want to give a brief introduction to probabilistic programming and cover some ideas which have some broad applications to, I believe, machine learning, classical programming, and some ideas in like Bayesian inference. And I think this will be a good introduction for some of the later talks we'll have this semester. So we'll try our best to just give lay some groundwork, and then hopefully we can go into more detail. So what is a probabilistic program? We'll talk a little bit about how to structure some computation using random number generators and sampling from a multidimensional distribution. And then I want to go into some data structures for how to represent multidimensional data and do marginalization and normalization in this setting. And then I kind of want to discuss compositionality. So how do you compose probabilistic functions to obtain a well-typed program, so that we can build a sequence of transformations and have some guarantees about the shape and the type of the output. And then so I want to wrap up with some sampling techniques, so ways to do efficient sampling, just some high-level strategies, and this will just be some review for many of you if you've already seen some probabilistic graphical models or simple random number generators. And then we'll talk a little bit about approximation. So that's the plan. And again, if there's any questions, just feel free to unmute yourself. So a probabilistic program can be thought of as a generalization of a deterministic program. So in deterministic programming, you have a direction, usually. A procedure takes some inputs and maybe some parameters that are either learned or specified by the user, and it outputs a value, a concrete string or number or other type of a deterministic value. Specifically, if you give it the same inputs and the same parameters, it will always produce the same output. And you can think of this as a type of probabilistic function where the distribution over the inputs is hard. It's a hard assignment. So the probability of getting a different output for the same input is 0 over multiple runs of this function. And this is assuming maybe some strict constraints. That is, there's no external state, there's no errors. This function is a pure function. So pure functions. And so usually what happens is that that you pass in some inputs and you infer these outputs, or you kind of do the computation, and then you get a specific output. And this is a directed data flow. In probabilistic programming, we can kind of go both ways. So you might have a program where you know the inputs to some approximate degree, and then you have a distribution or a belief over where they might lie. The actual values of x and theta might be a probability distribution, and you might have a specific function, say like a linear regression, polynomial regression, some kind of defined function that is like a static thing. And then you kind of push these approximate values through the function, and you get a probability distribution in our output space. So you have probability distributions on the input and a probability distribution on the output. Alternatively, you might not know the inputs or the parameters, and you'd like to infer this based on some observations. So you observe, or you condition on a specific value of y, and then you try to infer what the inputs might be. And so this is kind of a reverse or inverse of this classical paradigm, where you're trying to run this thing backwards to try to determine what inputs produce the observed outputs. Okay, good. So and this, while it's a pure function, can be stochastic. So from run to run, you might have different concrete values. You might observe different instantiations of these variables, but they have a there's no external state besides this random number generator, or the pseudo random number generator. So we call this a pure function as well. Okay, I want to do this in a little bit of a different order here. So I want to give an example of a probabilistic program, and then we'll go into like a specific application. So here is a simple Bayesian linear regression example. So you have some data or observations, and we have some uncertainty over our parameters. And so we'd like to, given this data, we'd like to try to infer which are the correct settings of these latent parameters, theta. So we have a normal distribution, and these have, say, some internal parameters that govern, the variant, the mean and variance, say, or if you have a different distribution, these are just parameters that are latent things. So we kind of give some belief over them, and then we'd like to try to obtain a better estimate of what the true value is given the observed data. So here we pass it through this this defined function. So here's our function. We assume it's a linear relationship between these variables, and then we try to either well, we have to score the observations. So this score function here tells us what is the likelihood of observing the data that we're seeing under this model that we've built. So somebody has written down a model that they believe to be true, and what is the probability of observing these data under this setting of the parameters. So here when we go to run this, what we do is we compile this. So this is compiled into a graphical structure, and this can be a probabilistic graphical model, or here we'll show just a simple circuit, so an arithmetic circuit with some primitive distributions. So here we assume that we have a function that can sample from the normal distribution and the gamma distribution. And here, what we'd like to do is obtain an estimate of, well, what is the likelihood of this data under the model. And maybe this isn't very good initially, but then we can update these parameters in our model, these thetas, using our favorite approximation technique. So we could use, say, like gradient descent, or maximum likelihood, or some form of approximate inference to determine what is a better fit for the data we observe. So we might go through a few iterations of this, and finally, then we can when we converge, then hopefully this will allow us to generate samples that were not previously seen in this data set. So this gives us a way to generate from possibly very complex distributions, as long as we have some estimate of what is the proper model. So someone has to write this down. This comes from a user. And in order to do this, well, you just need a few simple operators. And we'll show an example of how you can invert a distribution or a cumulative density function in order to obtain samples from simple distributions, and then compose those to a sample from more complex ones. Okay, so that gives us an idea a little bit of how these probabilistic programs can be executed on the deterministic machine. I want to give a simple example of one application where this might come up. So we have, say, a paper, right? Somebody's written a paper on arXiv, and it's an anonymous paper. You don't know who wrote it, and let's say you don't know really much about the domain, but you'd like to identify, well, who's the author, or trying to like what community wrote this paper, right? Is this a computer science paper or some other domain? So here we have a hypothetical example. Any similarity to real people is purely coincidence, and we have 3 users. So Mary is a statistician. She writes about kernel methods and other types of distance metrics and things like this. And we see this term in the paper. Well, it's a kernel method. So a kernel method might be different things to different people. For Mary, it might be a function that estimates, the approximate distance between points in some space, in a vector space. And for James, maybe this is like James is researching agriculture, so he's kind of interested in like what's some good ways to plant seeds and husk, some corn or something like this. So then we have our final user is Mark. Mark is a operating system software engineer. So he sees a kernel method and thinks, well, this is something to do with the kernel of your operating system. So anyway, we're just trying to determine what are the most probable sources of this document. And so we might be able to use this to do link prediction or authorship detection, right? So here we have three variables. So we have our author, and then we have these 2 words, kernel method. And then so we'd like to determine, well, what's the probability that a certain author or certain community generated this document, given that we see these 2 consecutive words. And so so here we can break this up into a product of 3 probabilities. So here is our joint likelihood, the probability of the author given these 2 words, and then we'd like to take the product of this and the probability of this kernel method being observed. So we have the probability of method given kernel. And then we have the probability of say, of kernel. And we like to determine, well, who is the most likely author of this document, right? So we have this data structure, which is it's an n-dimensional array. We can represent it as that one way of doing it, and each well, it's indexed by these three variables in our type system, in our data set. So we have the authors, which is a depth-wise kind of value here along the depth of this tensor, and then we have the vector, a square matrix, which is the vocabulary, and so this here, each face of this, we can slice into a set of transition kernels for each author, right? So so for Mary, this might be one sequence that you might see her write is, say, like kernel machine or kernel distance or kernel method and so on. And so so this represents the bigram probability of Mary writing these words. And then, you know, here you have you know, James and Mark. Okay. And so theirs might be slightly different. And then you observe this this sequence, right? So you accumulate these counts for, say, a large data set of documents that have been written by these authors. And then you'd like to estimate, well, for a given setting, which is a specific entry in this transition matrix, we know we're given kernel and method here. So we take the intersection of these to here, and this gives us a single entry in this cube. And then we'd like to do is normalize across all the authors. So we have 3 authors here. And so what we do is we take the probability of observing this pair of words for each author. And then you obtain a set of unnormalized probabilities, right? These don't sum up to 1. So in order to get the probability for each author, then we have to divide by the sum of these values. So this normalization is an important step in a lot of probabilistic programs. This is hidden from the users usually, but what this does is it will take an unnormalized vector. Here we have a vector of unnormalized probabilities, and then turns them into something that sums to 1. And so usually this is done in log space, right? So very often you have products in log space, and then you'd like to transform this back into linear space, and then do the normalization. You can do it in different order, but this ensures that it's numerically stable, because very often you might have large probabilities and small probabilities, and these don't really mix very well when you're using fixed precision numerical values. So, so you want to combine them linearly. So this is one example where it could be applied, and just these kernels here, these have some information about slices of this data structure. So you'd like to condition, and you'd like to be able to marginalize over some dimension of this data structure, and to collapse this into a single slice, a single face or a cross section of this cube, to obtain specific probability distributions for a given user, or say a given word in your vocabulary. So you could do this in any order. Say the user, you'd have to be able to support any kind of slice through this data structure. So very often it's efficient to store this as either a function which retrieves dynamically these values, or as a sparse matrix, which so you don't have to store all of these empty values that might be very inefficient to do that if you have a large dimensional, multi-dimensional array. Okay, good. So let's talk a little bit about what is a probability kernel. And so there's two kind of definitions of kernels. I think they're the same thing, but I'd be interested to know if someone knows the connection. But let's, so algebraically, if you have a mapping from some m-dimensional space to some n-dimensional space, or say, let's just say this is a scalar. So this tells us what are all the vectors in this space which map to 0. So you're looking at the pre-image of 0 inside of your domain here, and kind of intuitively, well, what this tells us is if you have some, say, like a linear transformation between these two spaces, then what is the set of vectors in this this space that are the same in our codomain? That is, if you just set this to the fixed value, then what are all the values that map to 0? And sometimes this is just a single value. So if you have a function which just maps 1, then this has some nice properties. Specifically that well, if this is true for any value inside the codomain, that is, it's a one-to-one function, then it'll be invertible. So you'll be able to go backwards from the codomain to the domain. So this kind of is a theme in probabilistic programming, where you would like to be able to go backwards from one function to another, and it's hard to do this if this kernel is well, the size of the kernel is greater than 1, because then you have it throws away some information. So so then there's this probability kernel, which has I think a generalization of this statement. So what we're trying to say is, given a space, a measurable space, call it omega here, our measurable space. And then if you take, say, two values or two dimensions in this maybe high dimensional space, then this gives us a product space. So we take this arrow, and this takes us to the product space. And this, well, this is a matrix or transition matrix that tells us how to get, what are the probabilities of transitioning from one point in that space to another. And crucially, this has some, well, this has to be normalized. So it is the rows of this matrix they all sum to 1. So if you want to picture here, then we can draw a little picture of the rows in this matrix. But basically, they're probability distributions. So each row, well, it's a discrete thing, so it'll be something like this, right? And then all of these values, P I1, P I2, P I3, all the way through PIN, these have to sum to 1. So we take the sum, J, into the size of n, then this equals 1. And then, so that's the probability kernel. And if we ask ourselves, well, we'd like this thing to compose. So you'd like to be able to take two matrices like this and then multiply them together. And these, this is a composition of stochastic, well, linear stochastic functions. So if you have a product of two matrices who are both valid stochastic matrices, then these have then these give us a new function. And so what is the type of this function? If you look at this in terms of a diagram, a sequence diagram, then we might have something that looks like this. So let's get rid of this thing. So if we have a function that takes two inputs, say x and y, and it just outputs a real number, you know, between 0 and 1, say, then this doesn't really work, because you'd like to be able to compose this with another thing that's, you know, z and q, which is another function. And here you have numbers that are coming out. How do you compose this into a new function? This doesn't, so this won't work. So so it turns out that you have to carry the input space forward. Well, you have to carry the I guess the dimensions of this measurable space. So you have a function which is, say, x and y, and you'd like to output x cross y cross this this number, right? So that way that way you have a space and a number that you can compose with another thing that's like, okay, so this, to be completely correct, should be x cross this score, and then y cross this score, right? And then if you have another thing that's z and q, we'll do it the other way around. Then this thing, well, it'll be inputs to another function here. So here we're just taking the product of these two spaces. Okay, so that's something that's kind of interesting. You have a function that carries the type forward in the output, and it so in order to do this and make sure that this is a normalized probability, you have to renormalize across each of these functions. Okay, yeah, so that's kind of just one way of thinking about a kernel in probability functions, stochastic functions. And what this gives us is ability to compose these operators, where each of these things, might be a simple or a complex function, as you'd like, on these two distributions. Now I'd like to talk a little bit about sampling. And there's lots of different ways of sampling from complex distributions. So just to start off with, I'd like to cover a few just simple strategies, and then we can think about how to do this in a higher dimensional space. So here we just have something that could be easily done. If you have a small enough thing to draw on a piece of paper, then the computer could do this instantaneously. But as we scale up, we'd like to think about, well, how do each of these strategies scale up as we add dimensions to this distribution, or we add, say, modes to our distribution. Then some of these strategies will have benefits and disadvantages. So to start off with, a lot of probability functions have this property where you're given the closed form probability density function. So we have this for common distributions, like Poisson distribution, and Gaussian, and Dirichlet. And lots of these have a closed form density function, and maybe they might have a closed form cumulative density function. But in order to sample from this, you need the inverse CDF. That is, you'd like to be able to take a uniform random number generator, which gives us, say we'll call this U, P, R, and G. And this gives us values along this axis. And what we really need is we need values along this axis to obtain samples. And so in order to do this, one way is to use this KS transform, or Kolmogorov-Smirnov transform. And what this does is, well, it's basically like either binary search or a Newton style search. So we generate a sample from this, and this is our target that we'd like to match. Actually, yeah, let's do this. So this is the inverse CDF. So this gives us this target, this Y star. And we'd like to approximate, well, what is the value that would be mapped to this Y star? And so at each of these points, we're going to do compute the gradient, or to just simply, do a hill climbing guess and check, and then this over time will converge to the proper value. So we kind of, if it's lower than the target value, then we adjust, we go, we increase, and then if it's higher, then we decrease, and eventually this thing will kind of cycle around and then converge to this target value. And then when it does that, then we have a sample from our distribution. So this is kind of like one of the simplest ways to do this inversion sampling. If you have a simple, usually this is done for a unimodal distribution, but you can do this for more complex mixtures of distributions as well. So this only works if this thing is strictly increasing. So so that's something to keep in mind. So if there's some flatness, or if there's some, well, it wouldn't be a probability distribution if it doesn't, if it decreases. But here you need this to be strictly increasing for this to converge. Okay, and the second way is to treat this as a directed acyclic graph, and say we know the transition probabilities from each of these nodes to each of the other ones, and you have the same generative process for sampling from the ancestor nodes, so the ones that have no parents. And someone's kind of given us this directed model. It could come from anywhere, but you'd like to be able to sample from this using this ordering. So you have a partial ordering over this graph, and this is basically just simulating the system. So so we draw uniform random samples, and then to sample from these nodes, we can use the inversion sampling technique. And then once these are sampled, then we proceed to the children. And you do this for each of the children, and then to obtain samples from their distribution. And you keep doing this until you reach the terminal nodes, or the leaf nodes. And then you can sample from this whole graph. And so this works pretty well, but it turns out that if you'd like to condition on some values, if you'd like to say set one of these, you observe one of these nodes, and this is fixed, and then this is before you do the sampling, then this is kind of problematic, because then, well, how do you, if this thing is fixed, then how do you obtain faithful samples from this distribution under that observation? And so there are different strategies for doing this, and some of these are more sample efficient than others. Let's just consider a naive strategy for how to obtain condition samples from this distribution. So if you have distribution which is highly skewed, it has like this this well, it might be a linear relationship, but the variance is the covariance between these two variables is high, right? So they're not independent things, but they have some correlation or covariance across this product space. Then, well, if we set one of the dimensions, so we observe this x here, then we'd like to be able to estimate what this distribution is. And well, one way to do that is just to simulate or to sample from the joint distribution, and then throw away everything that is not equal to this setting of the variable. So you might end up with many samples, but only very few that are equal to this observed value. And it'll work. It's just it'll take a long time because you're going to have to throw away many samples that are not equal to that observed value. So it turns out that this really doesn't work so well in large graphs or in distributions where there's a high covariance because it's very wasteful. So instead, what we'd like to do is have some kind of proposal distribution, which gives us, it might be specified by user, or it might be a function that is just uniform. So we have no prior belief of where the samples might come from. We just kind of set a uniform prior, and then sample from its distribution, and then weight those samples according to the likelihood that or the ratio of the likelihood from that distribution to the distribution that we care about. And this is kind of a little bit more efficient, right? Because you use all of the samples. It turns out that even if it's a bad proposal, even if this distribution is bad, it will converge to the correct value and expectation. It just might take longer. So you'd like to, so this P of X, right? This is say a set of counts for a discrete distribution. This doesn't even need to be like normalized. This can be the raw counts. And you're just taking the ratio of the number of the likelihood under your proposal. What is the proposal likelihood to the likelihood that that occurs in your counts from your raw data, and you score each of these samples by this ratio, and so this is like a weighted average. So each time you generate this, you compute this ratio, and then this will tell you the importance of that sample. So this is kind of a little bit of an art, but if you have a good proposal, then this will work well. If not, then maybe it's no better or even worse than rejection sampling. Okay, so then finally we have this this Markov chain approach where we model this this sampling process x1 through xn, as a chain, as a Markov chain. And so this is the same Markov kernel that we saw before, and so this also has a kind of a proposal and an acceptance or rejection step, and there are different variants of this that Metropolis Hastings or Gibbs sampling that have different flavors of how do you update the current state to find high density regions in this space. And if you have a good transition matrix, then you'll be able to cover all of the modes of this high dimensional distribution. And so so here we'd just like to obtain samples. And typically what happens is initially you'll have very bad samples. So initially the samples will be uncalibrated, and then so over time you kind of approach as this chain converges, you'll obtain increasingly good samples from the true distribution. So you say like throw away all the first ones, and then once there's some burn in, then you can converge, and then you accept these. So these are your samples from this distribution, and there's many variants of this. It has some very nice computational properties, but they all kind of so they try to address this issue of multimodality and how do you sample from a distribution in multiple modes. And in high dimensions, it turns out this may or may not be such a big issue, but the efficiency of these methods are really important. So a lot of thought has been put into this update step, so that making sure the transition covers where the distribution has support in this space. Okay, so that's kind of a brief overview of. So these are all they are exact in expectation. So over time, if you run this for long enough, now that might be to the end of the universe, or it might be in the next hour. It's hard to tell for some of these things, but they will converge in expectation to the exact value. So maybe you don't really care about that so much. Maybe you want to just get an approximate estimate or approximate density, and we hope it would be faithful to the true distribution that's in the data, but we don't have any guarantees. We don't want to make, well, so it turns out that there are some nice properties for these approximate density estimators. And if our distribution has certain structural properties, then it turns out that we might not need to do this exact style of computation. We might be able to approximate it. So finally, this is kind of just a very high level overview of approximate inference, but I want to just give a flavor of how this works. So if you have some kind of complex object in your input space and a transformation which maps this to a slightly simpler space of, so this M this is vector spaces, and then M is much greater than N. But for many objects that appear very complex, like images and graphs and so on, they're not full rank. That is, they don't have all of the dense. You can throw away a lot of information. Basically, it gets compressible. So you have documents and things like this. The distribution does not cover most of the. If you take a random object in this space, it's going to be noise, right? There's a very small subspace here that actually represents our data distribution. And so, so we could potentially throw out a lot of the data inside of this image or text and still obtain a very good approximation of this space. And so this is exactly what some neural methods like autoencoders try to do. So they compress this space into a smaller subspace, and then compute the distribution in this space, this latent space. And in order to do this properly, you'd like to have this distance metrics be preserved. So you'd like to have that 2 points that have some distance in your data space, then you'd like for that distance to be approximated inside your latent space. And for a distance metric, this has a few properties. So you'd like to have that it's strictly positive, and then it's only 0. So I think this is where the kernel comes in. This thing is only 0 where these two are the exact same points. So that means that you can't have 2 different points that map to the same point in your output space. That cannot happen. Then inside of this latent space, you'd also like to have symmetry. So the distance between one point and the other is the same as the distance between the other point and the first. So I guess that's kind of intuitive how we think distance works. And then there's also this Cauchy-Schwarz or triangle inequality, which tells us that it's a vector. It's an inner product space. If you have this, if you take the inner product, then this is going to preserve this this triangle inequality. Okay, so it turns out that for a lot of embeddings or these differentiable functions that are trained where the parameters are trained by gradient descent, then this thing is like a kernel, has these kernel properties. And specifically, there's this theorem, the Johnson-Lindenstrauss theorem, that says if we set an error, like if we say we'd like this epsilon to be a specific value, and you have a dimension in your input and a dimension in your output, then this tells us what is the maximum amount we can compress this data, assuming some sparsity structure on the input. So as long as this thing is not full rank, then it turns out that we can throw away a lot of those dimensions, project this into a lower dimensional space using a linear projection, and then this error will be bounded. So the distances in this projection, the projected space, are bounded. And this is exactly what this says. So intuitively, if you have a data set of some set of points, then we can project those into this lower dimensional space using this. Well, there's different tricks, but one of them relies on SVMs or kernel, the kernel trick. And here you have this distance is preserved in the lower dimensional space. So that tells us that it's possible to do approximate inference, and it still kind of makes sense, where this distribution in our latent space would be a good approximation to the true distribution, which we might not know how to sample from. So this P data is very complex, and so we'd prefer to do something a little cheaper inside of this space. Okay, yeah. So that gives us, I think, takes us pretty much to the end of what I wanted to talk about today. But what we saw was there are ways to compile probabilistic programs to structured graphs, where you have some user specified structure, and you can efficiently compile this into something that a machine can execute just using these few operators. So you have basically all you need is addition, multiplication, and well, division is kind of special case multiplication, but that gives us the ability to do very expressive things. Turns out that a lot of research today is looking into making this more expressive. So here you have finite dimensional, or well, this can be infinite dimensional, but each of the variables, like you can't have a random number of random variables, or if this is, say, like every random variable is connected to every other random variable, then this gets intractable. So so if you have like a deck of cards, then this is a classic kind of problem where a lot of this breaks down, is the number of possible decks in the deck of cards is much greater than the number of atoms in the universe. So being able to sample from this efficiently is kind of tricky. So there are different shortcuts to doing that. And then we saw how you can compose these simple functions of these primitives to obtain more complex distributions using sums and products. And here we saw that if we assign a type to this function, it carries the input type forward. So so this is kind of an interesting different type of function than you normally see. And then it also has to have this normalization at each step. We saw a simple application for authorship detection and link prediction. So here we have just a few examples of how you could represent this data structure, either statically or dynamically. You could recompute the counts. Usually this is stored in like a map or a dictionary, and then you can compute this multidimensional sum or product in an efficient way without having to store this v by a by however many dimensions you have array. And then well, we talked a little bit in the beginning about bidirectionality and how there's this inverse property. So you can invert some functions if they have this property. And so, for example, if you have a function where multiple inputs after a single output, then as you do in many stochastic functions, like in general, your whole domain could be mapped to a single point in the codomain, then in order to go in reverse, then you have to, well, you have to give a distribution over this whole domain. So this is kind of a feature or a problem that you have to work around. And so you could run this both ways to say, if you have some distribution over your parameters and you want to push them forward, or if you have some fixed parameters and you'd like to estimate the likelihood of seeing some data using this this reverse inference, or I guess inductive method. You want to induce some latent parameters. And then finally, yeah, we saw that there are some different ways to sample and to do this approximately. So I want to leave it at that. We have some very exciting material scheduled for this semester. I thought this would be a good introduction to some of the open research questions, or some of just the lay some groundwork for future speakers, and those will be posted in the Slack and on the website. So stay tuned. I think we've got a very exciting lineup. And so next week we'll cover a little bit about another type of calculus called the sequent calculus, and then after that we'll have a guest lecture from Professor Panangadan. We'll discuss quantitative equational reasoning, and very excited for that and the ones that follow. So thanks for tuning in, and if there's any questions, I guess could stop and